All right, everyone, and welcome to 5.2. So this is the big video for maybe the whole week. All 8 videos is the big one right here. Okay, so we're going to start off with a bunch of definitions, talk about how they work, see what's going on with some graphs, and then at the very end of the video, we're going to start with an example. Okay, so we need to talk about a few things before we can really get into anything. If we have a function, f of x is equal to some number, a sub n, times x to that power, plus another number, x to another power, that's one lower, plus dot 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 all the way down to what's called a linear term. This could look like 2x or 3x or negative 5x, some number times x, plus a constant. This is a polynomial function, okay? And again, there's a bunch of examples of this, and we've dealt with polynomial functions a lot, okay? You yourself have seen a lot of polynomial functions, even if we haven't labeled it like this, okay? So this is the precise definition. It's just a bunch of monomials, right? A bunch of numbers times powers of x's, okay? And specifically, n is the degree. N is that biggest exponent, okay, or the highest power. And then we say that a sub n x to the n, so that highest power, that n, with the coefficient, with the number next to it, we call that the leading term. And the side note is the leading term will not always be first. It should always be first, a sub n x to the n like this. But if this polynomial is not in general form, then it might not always be the first, okay? And then finally, a sub n is the leading coefficient. So 4 definitions to start off the video today. Leading coefficient, it's the number in front of the biggest exponent. Leading term, it's the whole monomial with the biggest exponent. Degree is just what is that highest power, and the polynomial function itself looks like this. Okay, so let's look at some stuff, right? Go to my good friend Desmos. It almost sounds like Desmond. It almost is kind of like a name. All right, I'm going to give you a polynomial. Let's say x cubed minus 2x plus 3 or something like that. This is a polynomial. This is a cubic polynomial. Okay, this right here is the leading term. 3 is the degree. Degree is that highest power of x. If I changed it to be like this, now the degree is 5. Even though it's not in general form, right? This x to the 5th should be at the very front. But even if I write it at the end, the degree is still 5. The leading term is still x to the 5th. If I do something like this, the leading term is minus 2x to the 5th. But again, we usually write it in general form with this leading term out in the front. Okay? And again, the leading coefficient is that number in the leading term, this coefficient -2. We'll do some more examples with this, but I just want to kind of show a little thing. So one of the things that we're going to talk about here is what's called end behavior. Any polynomial we have will always do something at the end. So for example, go back to this cubic. It's got some waves in the middle. But eventually, right, it's zooming off to infinity or it's zooming off to negative infinity in the y direction, right? Either shooting off into the top or shooting down into the bottom, okay? If I change this to x to the 4th, again, it's doing some stuff in the middle, but eventually, if I zoom out, right, it's just going off to the skies. That's what we mean when we say end behavior, all right? And we're going to notice some patterns here. Right? So if I turn this into a negative, Well, then now instead of going to positive infinity in both directions, instead of shooting up, now shooting down on both sides. Okay, and that's not going to be a coincidence. If it's x to the fourth, notice how it's going the same direction. Either they're both going up or they're both going down. If I change this to x to the fifth, well, now in one direction it's going up. I'm mirrored. In one direction it's going up, and in the other direction it's going down. That's not going to be a coincidence either. And again, if I put a negative in here, it switches. The stuff on the middle doesn't really matter for end behavior. All we care about is at the very end. I'm gonna show you guys a little table for end behavior, and then we're gonna go back to the graphs and really cement this in. Okay, so the end behavior only depends on the leading term. Okay, so here's a little chart that you can use. So if I have an even degree, something's gonna happen, and if the degree is odd, something else is gonna happen. If I have a positive leading coefficient, something's going to happen. And if the leading coefficient is negative, something else is going to happen. So if it's positive with an even degree, the end behavior kind of looks like a parabola. And this is how we kind of can write it. We're just going to write some squiggles in the middle because we don't care about what happens for the middle. This is for end behavior. Okay. What do we care about this function at the end? At the end, it's going to go up in both directions, like a parabola. If the leading coefficient's negative, again, we don't know what's going to happen in the middle, but now it's going to go down on both sides, like a negative parabola. Okay? If it's an odd degree and a positive leading coefficient, then it kind of looks like a cubic function. And again, who knows what's going to happen in the middle? Let's write some squiggles. If it's negative, the directions switch. So let's kind of visualize this with some problems. Okay, example 1. Let's use this table. We're going to find a bunch of different things. Find the degree, the leading coefficient. Wait, hold on. Leading coefficient. I have destroyed this word. Leading coefficient and end behavior for the following. All right, part 1 or part A, depending on how you want to phrase it. It's going to be f of x is equal to 3 plus 2x squared minus 4x cubed. Be careful. This one's not in general form. Why? Because the biggest exponent, x to the third, is not at the beginning. This is at the end. You have two options here. You can either rearrange it and put it to the end, or you can just say, all right, I know this right here. This is our leading term. I like to just underline it. It saves me a little bit of effort rather than put it in the right form. Okay, so the degree, that's the highest power of x. So our degree here, highest power of x, well, we got no x, x squared, x cubed. Highest exponent is 3. The leading coefficient, well, I already showed you the leading term. The leading coefficient is just the number that has that x. So the number here is -4. To find the end behavior, well, we use this chart. Is our degree odd or even? Let's try that again. Is our degree odd or even? Right? The degree is 3. The degree is odd, so we know we're somewhere over here. Is the leading coefficient positive or negative? Well, the leading coefficient is negative, so our end behavior has got to look like this. Let's see if we're right. All right, I'm gonna type this function in Desmos, and hopefully this has the right end behavior. 3 minus, hold on, I gotta switch. Right. 3 plus 2x squared minus 4x cubed. All right, let's look at what we had. We said our end behavior is it goes up on the left, it goes down on the right, and we said we don't care about what happens in the middle. It goes up on the left, down on the right. Is that what the graph is? Yep. To the left, we go to the up. the right, we go down, and something happens in the middle. We got a couple little mini waves. So we know we did it right. That's our answer. Right here. Do it for 3 more. For B. G of t is equal to 5t to the 5th minus 2t cubed plus 7t. Again, this one is in general form. The biggest exponent is at the front, which is nice. So our degree is what that biggest exponent is, which is a 5. Our leading coefficient is the number in front. That's also a 5, coincidentally. And our end behavior, well, our degree, we have to use the table. The degree is 5, so it's odd again. It's going to be one of these two. And because the leading coefficient's positive, we know it's going to be this one. It should look like that. Let's see if our answer is correct. We'll plot it. So it should go kind of like a cubic function at the ends. All right, so we got g of t is equal to 5t to the 5th. It's 2t cubed plus 7t. That's doing something weird in the middle, but just like we said, it's going to go up on the right and down on the left. All right, that's exactly what we had. Up on the right, down on the left. That's our right end behavior. All right, let's do 2 more of these to really just drive the point home. H of p is equal to 6p minus p to the 4th minus 2. This is not in general form. The biggest exponent of our variable is over here. Our degree is that biggest exponent. That's 4. The leading coefficient is the number next to that variable. Well, there's no number. Or is there? Right? You can think about this as a -1. And that's our leading coefficient. So this degree, right, is even. The leading coefficient is negative. We have to find even and negative on our table. Even's over here. Negative's over here. Like a downwards parabola. Okay? Should look like this. And again, who knows what happens in the middle. But at the ends, it should function the same as a downwards parabola. Let's see if we got it. Are we getting some sort of downwards parabola behavior here? Yep. Funky stuff happening in the middle, but on the ends, it's going down. Which is exactly what we said. Something's happening in the middle, but on each end, it's going down. All right, one more trick question before we finish the video. Again, this should be the longest video out of all of them. We have f of x is equal to 3x squared times x minus 1 times x plus 4. This is certainly not in general form. This is all factored, which is great for x-intercepts. But it's not so useful here. You have 2 choices. If you want, you could FOIL this out and then distribute the 3x squared, and that'll work. A lot of work, though. You don't have to necessarily do that. You can just count essentially all the x's for our degree. We have an x squared here. That'll eventually have to become multiplied by another x. That'll give us x to the 3rd. And we'll also have to multiply it eventually by this x over here. And there's a whole bunch of other stuff, but we only care about the biggest thing from each. Okay? We're looking at degree. So it's going to be 4x squared times another one will be x cubed times that last one will be x to the 4th. You can just, if it's all factored like this, you can also just add all of the exponents. 2 plus 1 plus 1 will be 4. The leading coefficient's a little tricky too, but you do the same thing. Just look at all the highest powers that eventually have to get multiplied. 3x squared times 1x times 1x. That'll be 3x to the 4th. So that leading coefficient is going to be 3. All right. And again, you can FOIL all this out and find these the more traditional way as well. This is just showing you a shortcut if you wanted to use it. So we have an even degree. We have a positive leading coefficient. So it's going to look kind of like an upwards parabola, like that. Let's see if we're right. Is the end behavior like an upwards parabola? Well, 3x squared times x minus 1 times x plus 4. Oh man, this has a lot of weird stuff in the middle, right? Oh, holy moly, how far down does this go? This goes down real low here. Let's get a better scale, shall we? Let's say -5. There we go. This looks a little better. It goes down very low. But again, at the ends, it's shooting up, which is exactly what we said. We don't care about what happens in the middle for end behavior. But on the very end, it goes up. And on the other end, it goes up. It's exactly what we have here. All right, and that's how to do these first couple of problems.